All right. Last time we talked about the difference between countable and uncountable sets. That's the last big thing that we talked about. So we looked at some common sets that appear in lots of places, and we asked questions about whether they are countable or not countable, uncountable, counter-countable, anti-countable, a-countable. English is a stupid language. Moving on. We found out that a lot of sets are countable, but some of them were not countable. So we came up with an interesting diagonalization proof for the set of real numbers between 0 and 1. We assumed we have them all listed. And then came up with a counter example, a proof by contradiction, basically, that said that assuming they're all there, we could add 1 mod 10 to each digit in each place. So the first digit of the first number increment mod by 10, the second digit of the second number increment mod by 10, the third digit of the third number increment mod by 10, and that new number that we're generating would be distinct from every number that we'd listed so far. And that was a way of showing that there is no way to enumerate this entire procedure. So we then looked at 2 different ways to possibly enumerate this set epsilon plus of A, B, and C. And we found if we did it in alphabetical order, we couldn't enumerate everything, but if we did it in length order, we could enumerate everything. So just because you make an assumption about how something is going to be enumerated does not necessarily mean that it can't be enumerated if you find that you fail to be able to enumerate everything with your assumption of a particular way. This is why we also overload comparable in a lot of things. Right? If we're going to be able to compare between 2 things, we might want to be able to define how things are compared in a language like Java. Maybe if with one particular kind of comparison, if the goal is to be able to enumerate some set, we need to define what it means to put them out in a particular order so that we can enumerate all of them. So we found that Turing machines are countable because binary numbers are enumerable. And since we represented binary Turing machines as binary strings, that we could then eventually output every possible Turing machine. We'd have an enumeration procedure where we just continue to spit out Turing machine after Turing machine after Turing machine that does something, that does something, that does something, whether it does something relevant or useful, we don't care. But now we have a process for continuing to generate new Turing machines that haven't been seen before. So they are countable. There are an infinite number of them, but there is a procedure to generate new Turing machines forever. Last random tidbit from Turing machines is going to be a concept called a linear bounded automata. We've looked at a bunch of ways to potentially extend the power of a Turing machine, and most of those fell flat and failed because we found that they were the same power level. But what if we wanted to limit the power of a Turing machine in an interesting way? First of all, why would we care to limit the power of a Turing machine if they're already solving anything that we can possibly write in a program? Why would we care to limit it in interesting ways?
Perhaps efficiency.
Yeah, efficiency is the big one. So the 2 big limitations of this that we've seen are a non-deterministic Turing machine. An NPDA is just a non-deterministic Turing machine where the tape is restricted to, rather than being all access all the time, it's treated like a stack. You can imagine that you couldn't go left from the topmost symbol or the rightmost symbol or the leftmost symbol, however you're organizing your stack on the tape. So you're treating the tape like memory. We can emulate a stack within memory. So an NPDA is just a Turing machine where we're treating the tape like a stack. If we limited the tape to a finite portion of the tape that says you have 10 cells, or you have 25 cells, regardless of what that finite number is, you end up with a DFA or an NFA. So now we're phrasing the classes of automata that we've seen so far in this class based on how would a Turing machine emulate that capability, or what limitations do we need to place on the Turing machine to be able to emulate that particular kind of language. So a similar question to that might be something like, we know that the input for a class of language like A to the n, B to the n could be arbitrarily large. We don't want to say infinite because the n is going to have a particular value for some string, but it could be A to the 1 billion, B to the 1 billion. If we treated this like a DFA or NFA, we would have to put a hard cap on the memory. Regardless of the length of the string, we only have this much memory, which is why a DFA or NFA can't work for something like A to the n, B to the n. You can come up with an n that is so large that our finite memory just can't hold it. But a linear bounded automata is going to be one in which we limit the memory to whatever the input held when we began. So if we had A to the 2, B to the 2, then we would be limiting ourselves to 4 spaces. If we had A to the billion, B to the billion, we'd be limiting ourselves to 2 billion squares, or 2 billion addresses. Does that make sense? So the amount of room that we have scales with the length of the string. But we can't use more than the length of the string. So as usual with Turing machines, there's still no bound on the actual size of the input. Any A to the n, B to the n for a particular n that you give me, the n could be arbitrarily large. The way that we would implement this is we have some special left end marker and some special right end marker that kind of are like bookends that the Turing machine's head cannot move past that, and no input can be written out there either. So the end markers can't be rewritten. You can't just make them go away somehow. They're read only, and the read-write head can't move outside of those bounds. We can make one more assumption that this is non-deterministic. And do note that it can still have multiple tracks, but each of those tracks is still bounded to that same size as the first track. So yes, we could have A to the n, B to the n, where n is a billion, but we could have a second track of a billion spaces to work with as well. Or a third, but there need to be a finite number of tracks for a particular problem. Any questions about the setup of a linear bounded automata? Let's see an example. So could we come up with, this is not asking you to do this necessarily, but could we come up with a linear bounded automata that accepts the language A to the n factorial? What do we think? Do you think the answer is yes, or do you think the answer is no? If the answer is yes, at a high level, how would you set it up? If the answer is no, have some kind of logical explanation for why you think it's not.
Maybe yes, for like the same thing you mentioned earlier, where like if you set a, let's set a bound that you were arguing earlier, that if you had like A to the n, B to the n, you said, hey, we're doing just, 2 or a billion, then there's like maybe that cap if it's linear bounded, which I think that was what's happening in the other example, then this is also linear bounded. So if you set n to, let's just say 5, then you know that you're working with like something 25 or
I think it's 120.
sorry, 120. Wow. Oh, no. Anyway, point being, you'd have a tape that's 120, and so that's what you would be manipulating.
what would the algorithm kind of look like at a high level? So you have 120 A's on a tape with exactly 120 spaces. You can have an extra track or a few extra tracks of size 120, but what would that look like to be able to determine, yes, 120 is some factorial?
You could have multiple tracks of size 120
Yeah,
for just 5 factorial.
yeah. So I'll give you a hint. Yes, this is linear bounded. And you would want to use exactly 2 tracks. What would go on the second track? Yeah,
Well, since you're doing like factorials, perhaps it's, I don't know, I was assuming you'd have like, maybe you'd be doing the result, like. I don't explain it, but. You have to do 1 times 2 times 8 times 4 times 5.
yes.
So like the things for times 4 would be, let's just say the top tape, and maybe it's the result of times 5 is on the bottom tape or something like that.
Okay, that's a very good, that's good intuition. We want to break the factorial down into its components. 1 times 2 times 3 times 4 times 5.
Could you just be like calculating the factorial on the bottom one pretty much? And then. I guess.
How would you do that?
I'm not sure.
I think this is the right track, no pun intended. But instead of multiplying, think about dividing or dividing out common factors. So we know that 120 is divisible by 5. It's divisible by 4, it's divisible by 3, and it's divisible by 2. So could we keep track of something like, start with the number 2, you have 2 of something on that second track. We have a way of counting that to figure there are 2 things on the bottom track. So we can now go to the top track and take every other character and turn it into something that we've seen before. So we would have something like AX, 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 AX. We got rid of half of them. We then go down to the bottom track and add something so that we have 3 of something. The remainder, after we divided 120 by 2, we would have 60. 60 is still divisible by 3. So you would now go every third element, and basically the process you'd have on the bottom track is I'm gonna go first, second, third, back to the first. When you go back to the first, you go to the place that is stored on the top track and change something. And then second A, third A, first A, change it. Second A, third A, first A, change it. And then you would factor out the every third A, and then you would be left with 20. Then you would factor out every 4th remaining A. Then you would factor out every 5th remaining A. What's your termination condition?
I think if you reach, would it be the last A and it is the last, like. Yeah, pretty much it just if you reach the last A.
Yeah, if you finish a process of going through the top and changing and dividing out some number of A's and you end up with a single A left. 1 A left would mean that the number that you started with was a factorial.
So, well then, are you leaving the A's that like are not the multiples?
Yeah,
I guess.
yeah,
So
you'd start with 120 A's, and then you would take every second A and turn them into an X.
So then on the last step, you would have 5 A's though, and then you would just go to the last one.
And then you would divide by 5. You would take out 4 and leave 1. Basically, you're doing a division of, you take 120, you divide it by 2 to get 60. You divide that by 3 to get 20, you divide that by 4 to get 5, and you divide that by 5 to get 1.
Okay, I was just thinking logistically, because at the last step you have 5 A's and you go to the 5th A, so you're at the last A, and then
Yeah.
you would remove that one. So you still have like 4 A's left in the middle, but you're on the last day, so you know you'd be terminating.
Sorry, you're flipping, leaving.
Oh, so
Yeah,
you're
yeah.
leaving the ones that are like.
Right, yeah, the ones that you're factoring out. You're getting rid of all of them except the one that is, yeah, you're taking the original 120. Half of what's left, 1/3 of what's left, 1/4 of what's left, 1/5 of what's left, and then you end up with a single A left on the top tape.
Some of this have a lot of states.
Oh, yeah, this is why we're not drawing this out. It would be very complicated to draw this out, but the question is just, is it possible to do so? And what is this associated class of language? And is there a level of efficiency that is different from the language of everything a Turing machine can do? So we're going to successfully divide the A's on the tape. If at the end of one of these processes, a single A is left on the tape, then we know that the original number of A's was a factorial. So we did need that second tape to keep track of the current divisor. Don't worry really about what the transitions would look like. That would be quite the process. But the more important question is this more or less or equally powerful compared to NPDAs? Not Turing machines, but NPDAs. Is this more or less or equally powerful to using a stack on an infinitely long tape? Thoughts?
I mean, my intuition says it's more powerful because we can move around the tape, we don't have to act like it's a stack.
Mm-hmm.
But I also don't know if that in reality gives more power or not, because.
It's good intuition.
Yeah.
Because you get as much tape as there is input, so it scales pseudo infinitely. You just can't take an input and use way more input than that as part of its computational process. Who thinks it's more powerful than NPDAs? You do not have to be right. It's okay. More powerful than NPDAs? Less powerful than NPDAs? Equally powerful to NPDAs? The answer is more powerful. And the reasoning for this is we can show that there exist multiple languages that are not accepted or not possible to produce an NPDA for. And you can use the context-free pumping lemma to show that something like a to the n factorial is not context-free. And yet we can build an automata to accept it if we use a linear bounded automata. How about unbounded Turing machines? Are they more or less or equally powerful to unbounded Turing machines?
Equally.
Who thinks they're more powerful than unbounded Turing machines? Less powerful than unbounded Turing machines? Equally powerful to unbounded Turing machines? The answer is actually less. So basically, we can, with an infinite amount of tape, we can process things that require a lot more memory to produce in a way that doesn't scale linearly. Maybe you need a quadratic amount of extra space, but you basically need to set the number of tapes that you have at the beginning. So it's a finite number of tapes that says, for a linear bounded automata, I can't just have an infinite number of these, and it is set it at a finite number. And there will be some unbounded Turing machine that you could construct that needs more memory to solve for a particular language than just that finite number of tapes that are as long as the associated input. The full proof of that is in the book. You're welcome to take a look at it, but I find that kind of intriguing, just trying to compare the intuition of different levels of languages, because it's not fully intuitive sometimes, and you really need to look at the proofs to be able to understand why this makes sense.
Is this like kind of going back to like the simulation thing of like that other thing can simulate this thing,
Yeah,
but it doesn't Yeah, so you'd be simulating that, and so it could be, it's more powerful, but like, we're doing the same thing essentially.
Yeah. Yeah, but being able to say that, not just for a particular language, can we simulate it for a particular language? Yeah, can we construct a linear bounded automata in an unbounded Turing machine? Can we construct an unbounded Turing machine for any problem inside of a linear bounded automata? And that's what breaks. All right, end of that slideshow. So we've kind of been hinting at this, but we're now going to bring it all together and come up with an actual hierarchy of languages, of classes of languages, so that we can actually visualize what are all the different kinds of languages, the different classes of them, and how do they interrelate to each other. So we need some way of distinguishing between these classes of languages. They can have particular practical uses or theoretical uses as we look into this. So we're going to look at a couple different classes here that intrigue us. One way that we could manipulate this is by looking at a Turing machine and making changes to and figuring out what a Turing machine can operate on and cannot operate on. And another removes all restrictions from grammars. I lied to you slightly for good reason when I introduced context-free grammars and said there are no restrictions. There actually was a restriction to a context-free grammar. Does anyone intuitively know what that was? What was the restriction to a context-free grammar? I didn't say there was one, but there was. I'll let that cook for a bit. So there are two more kinds of languages that we might care to reason about that are more general than just Turing machine. So a language is said to be recursively enumerable if there exists a Turing machine that we say accepts it. When we say accepts, that's not accepts or rejects, that is just accepts. It is undefined what happens to a string that is not in the language. The Turing machine will not accept that string, but it may enter an infinite loop. And there may be no such way to avoid going into an infinite loop on some strings that are not in the language. So if a string is not in the language, we will just say going into an infinite loop is fine. And the class of that language is recursively enumerable. So this is defined to say for every string that is in the language, the Turing machine will be able to determine that it is in the language in a finite number of transitions. For anything not in the language, the Turing machine may reject or it may enter an infinite loop. We don't know. Note that this means that something like the membership algorithm doesn't exist for this class of language. We can't determine yes or no a string is in the language because we may never be able to answer the question, no, the string is not in the language. If our Turing machine enters an infinite loop, then we don't know whether it's just waiting to accept the string and it's just a really long computation, or if it eventually will halt and accept, or if it will just never stop at all and keep spinning and keep spinning. Questions on recursively enumerable languages? We'll cover this in a lot more detail in a bit. Yeah.
What was the restriction you said about the context-free language?
We haven't done it yet. I haven't, that spoiled it. I'm letting that cook for people to think about, wait, what?
Okay.
We'll get there momentarily. The second class of language that we care about is a recursive language. So this is a class of language where if we build a Turing machine for it, it will accept every string that is in the language in a finite number of steps, just like a recursively enumerable language. But it also rejects everything that is not in the language in a finite number of steps. Note that we're also restricting this to the same input alphabet. So if our input alphabet is AB and we feed it the string CCC, that is undefined. We don't care to reject that string because it's not in the input alphabet. So you give any string that utilizes the input alphabet, we can determine yes or no, we accept or we reject in a finite number of steps. So a membership algorithm exists for every recursive language, and a membership algorithm doesn't necessarily exist for recursively enumerable languages. Do note that there are some algorithms where being able to answer yes or no takes a very, 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 very long time. The example that I like to give for this is bozo sort, which is the concept of, if we've heard all of the possible sorting algorithms and data structures and algorithms, my absolute favorite one is bozo sort, because you just randomly shift everything around and then check and see if it's in order, and then randomly shift everything around and check if it's in order, and then randomly check. So let's say you pass an array of size 10,000 into bozo sort, and you're just going to randomly shuffle everything around, check and see if it's in order. When's that going to terminate?
Can't really tell, unless you won't do the same, like, shuffle twice.
I mean, it's not guaranteed to, but I mean, eventually it will, right?
Can't say that for sure.
You can't, but let's say it's been spinning for 10,000 years. Is it gonna terminate?
Maybe.
Maybe. Let's say you don't know what the algorithm is, and all of a sudden now you're looking at a Turing machine that has been running for 10,000 years. Is the algorithm that it's using bozo sort on a really long array, or has it entered an infinite loop? From the outside, we can't tell.
That was called bozo sort.
It might be.
It is called bozo sort, but I call it bozo sort because no one should ever write it.
All right,
I did quickly, I have changed the name of
that's fair.
it. So here's an interesting question. Are all recursively enumerable languages recursive?
Yes,
Why?
because they have the same restrictions, except one, like they're. Like the recursive is a subset of recursively enumerable, or, sorry,
Yeah, no, you're right, but I think you flipped the idea here. So recursively enumerable languages can't have a membership algorithm, so are those a subset of the recursive languages? The answer is no, for the exact opposite reason. But are all recursive languages recursively enumerable? The answer is yes, for the exact reason that you gave. So if we can generate a yes or no answer, that's a subset of we can answer yes, but not no. Does that make sense? Why there are subsets?
Why were they recursively enumerable? Languages recursive again?
So our recursive language is recursively enumerable. Recursively enumerable is all languages where we can say yes, and it's undefined what happens when we say no. So if we're able to say no, that's part of that undefined behavior. We don't place a restriction on what happens when we say no. So recursive languages that always are able to say no is part of that undefined. We don't need to define that, even though we can define it, if that makes sense. It's like how all regular languages are a subset of all context-free languages. There's an additional restriction placed on the regular languages. There's an additional restriction that's placed on recursive languages, but recursively enumerable languages are the biggest circle that everything could possibly be in. Because we basically are able to say, we don't care to define what happens on the no, we just need to be able to say yes for strings in the language. Yeah,
I'm a little confused about bozo sort being like recursive, because it says that it needs to accept in a finite number of steps, and you can't guarantee that it'll accept ever. So I don't, would that still be contained in like the group of things that can be accepted in a finite number of steps?
you can, yes, basically, you can become 99% confident, you can become 99.9% confident, you can become, basically, you take the limit as you get arbitrarily close to, and that limit becomes infinity. But you can become arbitrarily close to perfectly confident that it will terminate in some number of steps.
And that's good enough?
That's good enough.
Can't guarantee that it ever will. Like ever will, shuffle into the properly sorted.
It is, that's a question worth asking, right? We don't know for sure that it's ever going to terminate, but the idea is it will eventually terminate. If you give it an infinite amount of time, it will terminate.
Yes, that's true.
Yeah,
Okay, never mind.
yeah. If you set it at an arbitrary cutoff point, there's no guarantee that it terminates. But if you take the amount of time and you just give it forever.
You guarantee that it'll halt in forever though? I feel like we
Yes.
still can't.
Yes. Because forever is not a finite amount of time. Because it can halt, it will halt.
You mentioned like the 9 repeating thing, and like there's a math proof of like 9 repeating is eventually like a 1. So it's
Yeah.
kind of like the same premise.
Yeah.
Okay.
Yeah, you give it an infinite amount of time and it will halt. If you place that cutoff at 1 trillion years, if you place that cutoff at the largest number that I could possibly write, if I just started writing 1 0 0 0 0 until I died, if I place the cutoff at that many years, there's no guarantees, but that's also not forever. So how do we go about enumerating recursive languages? So we want to be able to define some kind of enumeration procedure. We have a recursive language. How can we enumerate all strings that are in the language? And the answer is to design a Turing machine. Since it's a recursive language, we know that a membership algorithm must exist for it. So we're going to call this Turing machine TM membership. The book uses much less descriptive terms than membership, but where possible, because we're going to start getting into very confusing feeding Turing machines to other Turing machines, a Turing machine that's going to be called M, another Turing machine that's going to be called M hat, another one that's going to be Turing machine M sub something. I don't like all of that terminology, so where possible, I'm going to give some kind of descriptive word for what this Turing machine does. In this case, this is TM membership. This is the Turing machine that is responsible for the membership problem of a recursive language. It will be able to answer yes or no to whether or not a particular string is in this recursive language. Does that make sense? Turing machine that answers the membership question. We're going to design another Turing machine that we're going to call TM generator. It's going to be able to generate strings that are in the language in what we're going to call proper order. And proper order for the language that consisted of the input alphabet ABC before was in length order. There exists a proper order that is going to be able to eventually output everything in a recursive language. So we just define what that proper order is, and then we begin creating strings that are in the language with TM generator. TM membership is going to be able to parse all of the strings and determine whether or not they are. So basically, you have TM generator write its output onto TM memberships tape. And then TM membership is gonna write onto the output track only those that it accepts. So the generator is gonna generate all possible strings. And then the membership is gonna take each of those strings and determine, yes, it is in the language, or no, it's not in the language. And after you filter all of that through both Turing machines, you have the list of strings that are in the language. Does that make sense? All possible strings that could be, according to the input alphabet, feed those into the membership. Membership determines yes or no, they're in the language. So for any recursive language, this will just start spitting out strings that are in the language. Questions on this process? If we can do this for recursive languages, can we do it for recursively enumerable languages? What would happen in a recursively enumerable language if we took this procedure?
If there was any string it wouldn't accept, it could possibly just go into an infinite loop and then to the next.
So TM generator will still be able to find every possible string that could be in the language based on the input alphabet. But TM membership is going to spit out strings, yes, 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 until it hits the first no that puts it into an infinite loop. And then it's going to just get stuck there. And we're going to be done being able to output new strings because our core membership Turing machine is stuck in an infinite loop, with no way for us to know whether or not it's eventually going to halt and accept and write something on the tape, or if it's stuck in an infinite loop. So we need some kind of new procedure that's going to allow us to figure out strings that are in the language without considering a string that may put a Turing machine into an infinite loop. So the goal is just to be able to accept every string in a recursively enumerable language. So how can we do that? Some rejected strings are going to cause the membership Turing machine to go into an infinite loop. This means there will be some string out there, probably many strings or infinite strings, that need to be accepted that we'll never get to. Can anyone think of a way that we could do this? Yeah.
I mean, you have to place a restriction. I don't see another way to do it. Like you just like, hey, if you go over some sort of like a loop that's over 1 million, just terminate or like halt or whatever, do the next thing.
We're not, if we do that, we're not guaranteed to get every string that is in the language.
Right, and that's I thought what we're supposed to be saying, like
We
some.
want to be able to enumerate and continue forever spitting out strings that are in the language. But there might be some string that is in the language that requires the Turing machine, regardless of the limit that you place on it, that will require more steps than that to be able to accept.
Could you like parallelize an infinite amount of times to start with every of the infinite amount of strings?
You cannot. That's a good idea, though. It turns out that it's very similar to something that we've seen before, which is why I introduced it to you in the first place. It was in our aside. And the process was the iteration of rational numbers. Because a rational number is basically recursively enumerable, right? We can continue to spit out new rational numbers, but to be able to determine something like, is pi a rational number? We need to spin and spin and spin and spin and keep generating new digits of pi to determine, is there a repeat in here somewhere? If pi is not rational, we will never be able to say, no, it is not rational. We know the first few trillion digits of pi, and according to the first few trillion digits of pi, it's not rational. Does that mean that it's not rational? No, it just means we haven't found it yet. We'll never be able to answer the question yes unless it is. So how did we figure out and enumerate rational numbers? Yeah, we had some kind of diagonal. So here's exactly what we're going to do. We're going to list an infinite number of strings that could be in the language, W1, W2, W3, W4, and we're going to simulate up to, but not including, a certain number of computations. So we're going to do the first move on W1, just the very first Turing machine move. See if it accepts. Then we're going to do the same thing for W2. Then we're going to simulate the second move, up to the second move on W sub 1. And then we're going to do the first move on W sub 3, up to the second move on W sub 2, up to the third move on W sub 1. Does this make sense? If it spins forever, we're only going to be looking up to the first some number of moves. We're going to keep incrementing that by 1, but only after we've considered the next string. So if we use this procedure, eventually, even though this will take a very long time, we will be able to output every single string that is accepted in a recursively enumerable language in some finite amount of time. Or sorry, given a string, it will be accepted in a finite amount of time. If W sub 1 spins forever, enters an infinite loop at some point, we will be stopping that process after some number of moves to consider new strings. So this works in the same way that rational numbers work. If any of these are accepted in a finite number of moves, we'll eventually get there. If they spin forever, we will continue to look at them, but not sequentially. We're not waiting to answer yes or no. We're just simulating the next move on each string as we diagonally start looking at more strings and longer iterations, longer letting them run. So it's a very theoretical concept, but this will work. This will allow us to be able to spit out new strings in a recursively enumerable language. Questions about this process?
Eventually, every string is possible. Yes, and then it just goes back.
This is the kind of material that when I first saw it made my head jump. It's just like, whoa, okay, wow, that will work, but it's highly inefficient. But the fact is, it's possible to do. So that is the basis of recursive and recursively enumerable languages. But now let's also consider, are there languages that are not recursively enumerable?
Is it uncountable
Yes,
stuff?
yes, anything that is not countable is not recursively enumerable. Right? We determined that something like the real numbers between 0 and 1 was an example of something that was not countable. There was no way for us to continue to spit out new values, new real numbers, such that for any real number that you give me, I can tell you how long it would take for this algorithm to spit it out. We have ways of spitting out an infinite number of real numbers between 0 and 1. We said that if you do it in length order, 0.1, 0.2, 0.3, 0.4, all decimals of length 1, then all decimals of length 2, then all decimals of length 3, then I say, when will you spit out 1/9? And it will never do so. So that's what we mean by not countable, is you should be able to feed me any real number. And if I have an algorithm that is recursively enumerable, I should tell you how long my algorithm will take to output that number. There is no such way to output something like 1/9 as a real number. Yeah, you could start doing all rational numbers between 0 and 1, but then that wouldn't hit other numbers that go on forever between 0 and 1 that are not rational. So languages that aren't recursively enumerable, all real numbers between any lower bound and any upper bound. I just talked about why we can't enumerate this. Let's get another example, just because real numbers is a single example, it might be nice to see some additional examples of some not recursively enumerable languages. Assume we have an infinite countable set. Give yourself a couple seconds, think of one in your head. What is a countable set that is infinite? Yeah. Integers, right? Positive integers, you can even say. Think about the power set of that set.
Power setting.
The power set means basically you're coming up with any possible subset of that set. So if we're looking at all of the integers, then we have the set that contains 1, the set that contains 2, the set that contains 3, all the way infinitely of all sets of size 1. But then you could also have the set that contains 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. That can go to forever. 2 and 3, 2 and 4, 2 and 5, that can go forever. All of the sets of size 3, 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6, continue that forever. Is it not countable? Why?
Because if you start enumerating, you're never gonna reach the sets of size 2.
In that way, but is there a way to diagonalize that? Is there a way to do that? Another way to think about it is if it weren't recursively enumerable, then maybe we could set up some kind of diagonalization proof like we did with the real numbers. What would that diagonalization proof look like?
Couldn't you do the same diagonalization? Well,
You could. It actually is exactly the same kind of proof. So yes, this is not recursively enumerable. So basically, you're going to start with an infinite binary table in 2 dimensions. Rows represent elements of the power set. Columns are strings in the original language. Cells represent whether a particular string is in the original language is in this element of the power set. So it looks something like this. So rows are elements of the power set. Columns are strings in the original language. So is this string in the original language an element of the power set? And we will see that if we flip each bit, in the first row, we flip the 1 to a 0. In the second row, we flip the 1 to a 0 in the second column. In the third row, we flip the 0 to a 1. If we continue this diagonalization proof, flipping each of those bits, we will generate a new set, basically, that was not in this original counting from T sub 1 to T sub whatever, it's infinite. But we'll be able to generate a new element of the power set from this way. What does this mean for us? What do we take away from this? If we apply this to Turing machines and languages, we will find that even though there are an infinite number of Turing machines, there are some languages that Turing machines cannot simulate. There are more possible languages than there are possible Turing machines, even though there are an infinite number of both. So that's interesting and strange, but it means that there are languages that Turing machines cannot accept. So the real numbers is one such language. The power set of an infinite countable set is another possible language. That completes the proof, basically, that some languages are not recursively enumerable. We'll come back on Monday and talk some more about this, but we're some of the way done. There's a lot more to parse here, but. To me, this is really interesting, mind-blowing stuff. Have a good weekend, try not to have nightmares about infinite sets. Hey, if you don't wake up, maybe you don't want to be someone who's dead, just stuck in an infinite nightmare. Yep.
Yeah.